Oh, hello everyone. Hello everyone. This video I'm going to demonstrate one of your homework problem in Excel loading. This homework problem, maybe because it has some math in there, mathematical distribution in there. So that's why some people think this kind of difficult to solve. Okay. Okay, let us see the problem description. He say actually it's a very simple problem actually. So the bar has a cross section area. So it give you a cross section area, and it give you yeah, it's a kind of special here. Yeah, he said he give we apply a distributed loading along its length. So we apply a distributed load, okay? And the distributed load at x equals 0, the load intensity is 0, but at x equal to 1.5 meter, the load intensity become a 9 kilonewton per meter. And determine the average normal stress in the bar as a function of x between the 0 and 0.6. Okay, so that's what this problem want us to determine. So I want to determine average normal stress. So normal stress. Okay, let's start with. Okay, I want to us calculate normal stress. The normal stress. Okay, let's see. How to calculate the average normal stress? Okay, the normal stress we already know is equal to the normal force divided by the cross-section area. And this problem already gives you the cross-section area 400 times 10 to the power minus 6 m squared. So the only thing you need to have to calculate is just your normal force. And where is the normal force? And he said between x between 0 and 0.6. So that means this region. And how to determine the normal force in this region and also as a function of x? I think that's maybe this is a difficult part for you. Okay, so we have determined. Okay, so we just use the same skill. Okay, we use the cosine. Want us calculate the normal force as this region. So okay, we cut section here. Okay, so and then we do the analysis on this cut section. Okay, so cut section, let us see. Okay, I cut section here. Okay, here and it apply a 4 kilonewton at here, and it's applied 8 kilonewton. Yeah, this is between. Okay, maybe apply 8 kilonewton here. So here is let me see 0.9, and here is 0.6. This point is 0.6, and the distance here is 0.9. So here will be 1.5. Okay. Okay, so okay, so we left here. Here he draws a small arrow here, but you see the arrow is gradually increase in magnitude. So that means a distributing load. Okay, so let's draw this distributing load. Okay, so we use the same cut section method. Okay, so in the cut section here, there must be a normal force here. Okay, there must be a normal force. And if I don't know the direction of normal force, I just assume everything is tensile. Okay, so the same thing, we have to do the rigid body equilibrium at this cut section. So let's do the rigid body equilibrium at this cut section, because everything is static in this textbook or in this course. So let us do the rigid body equilibrium on this cut section. So if we have normal force point to the left, so we have minus m. And we have the 8 kilonewton point to the right. So yeah, we use kilonewton as a unit. And we also have the normal force 4 kilonewton point to the right. Okay. Okay, so is that it? No, because yeah, you see, we have a we have a distributing loaded. Okay, so we have something distributed loaded force and add them together, and then it will become a zero. Okay, that's the rigid body equilibrium. So the problem is, what is the force for the distributed loaded? Okay, what is the force for distributed loaded? Okay, so let's continue finish this free body diagram. So we assume here we are at the this 0.6, and this is x. Okay. We just assume the position here is x, x, x. Okay. Okay. So how to find this? How to find this loading force from the distributed load? Okay, he give you the distributed load. He give you the distributed x equal to 0. X0 is 0, and x equal to 1.5. It will become a 9 kilonewton per meter. Okay. So I think this just tell you like this. Okay, that's first one. Okay, maybe just draw it here. For x equal to 0, it's 0, and x equal to 1.5, it will become 9. Okay, so it will become a 9. Don't forget its unit. It's kilonewton per meter. Yeah, it's an intensity. It's a newton per meter. Yeah, it's not a force. Yeah, be careful. It's newton per meter. It's not a force. Okay. Okay. So, and I believe it's linear. Okay, and here is x. Here is x. Okay. So, refresh just recall your memory. So, if you have a distributed load, if you have distributed load, distributed load, and how to find the final, if you have distributed load, on how to find the resultant force, how to find the magnitude of resultant force. If you have a distributed load, okay, and how to find the magnitude of resultant force. Just recall your memory. Yeah, we have you must learn this before in your class. Okay, yeah, but I think most of you will forget about this. Okay, so we have a distributed load function. Okay, so how to calculate the magnitude of resultant force? Yeah, remember that? Ring a bell. Okay, how to calculate the area under the curve. Under the curve. On the area under the curve. Remember that if you have distributed load function, how to find the magnitude of the resultant force, area under the curve. Okay. And now the range we care is from x to 1.5. Yeah, because we cut section here, so that means we calculate from the right. So we care everything from the right. So we cut the section here. Okay, so we are interested in this area. We are interested in area. So if you have, so P is that is the P. That is the P. That's P we are going to solve. Okay, yeah, we calculate from the right, so we care everything from the right. So we have this area is the area we are interested in. Okay, how to calculate this area? Okay, so it's very simple. It's a straight line. So it's from 0 to 9. So here must be 6x. Okay, so see 6x. So how about what's the area? First is the P. Yeah, so you know how to calculate. Okay, so this is 6x plus 9. That's area for trapezoid. Okay, 6 plus 9 and times 1.5. Yeah, this is 1.5 minus x. 1.5 minus x. And divided by 2. So that is our P. Understand? Okay. So what is our normal force? Okay, our normal force. Don't forget what's the normal force here. The normal force is just equal to 12 plus P. Okay, let's calculate what is our P. P is equal to, yeah, divided by 2. Okay, so it's 6. So this will nice x, nice 9x, 9x minus 6x squared plus 13.5 minus 9x. Really? 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 Did I calculate wrong? So, okay, it's cancel out. So we will have the 6.7675 minus 3x squared. Okay, so what's our normal force? Our normal force is equal. So our normal is 12 plus p. So it was 18.75 minus 3x squared. Okay, so that's our normal force and this section. So between in x between 0 and 0.6. Okay, so what is our normal stress? Okay, we give you the area 400 times 10 to the power minus 6. So it's 18.75 minus 3x squared. And be careful, this is kilonewton. Be careful, the units. Be careful, this is kilonewton. Be careful, kilonewton. So we have 2 times 10 to the power 3. Okay. Yeah, I think you can. Let me see. 10 to the power 3. So after the sum calculation, I think it will have the answer 46.9 minus 7.5 x squared. And its unit is mega Pascal. Okay, mega, capital M, mega is 10 to the power 6. Okay, so this is a distributed load problem in axial loading. Yeah, I think just you have to recall the memory. Okay, what is your resultant force? If you have distributed load, and what's your resultant force? Area under the curve. Okay, so here's the demonstration of homework problem. Okay, I just stop the video here. See you in another video. Bye bye.